Hi everyone. Up to now we have looked at sampling and types of data. We've looked at graphical summaries and numerical summaries. Now next up is probability, and the section on probability is divided up into these four parts. Now the first part, which is under probability, will be events. Now we need to be able to define events before we can define probability. And along with that, we're going to do counting techniques as well. Right, now first of all, the outcomes for this session. Very important, as always, you must know the definitions. Secondly, you must be able to identify events and word problems. Thirdly, you must be able to list and visually illustrate events from word problems. And lastly, you must be able to apply basic event operations. Now, if we look at events in general, things like weather forecasts, rolling of a die, flipping of a coin, then for weather forecast we'll say things like 20% chance of thunder showers tomorrow. And when we roll a die, we'll say 1 in 6 chance of rolling a 5 or a 4 or a 3. Or when flipping a coin, we say 50% chance of throwing a head or 50% chance of throwing a tail. So what we're trying to do in these cases is we're trying to quantify uncertainty. In other words, we're trying to measure the uncertainty of these events. Now, what do we mean by the uncertainty of these events? Well, weather prediction is not an exact science. Things can change. Rolling of a die. We don't know what outcome we're going to get when we roll it. We can list the outcomes, but we don't know exactly which one we're going to get. And the same with flipping a coin. Now, this process can be described as follows. We perform a task or a random experiment. Okay, this random part is very important. So we perform a task or a random experiment and we observe what happens. Now, we cannot predict exactly what the specific outcome is going to be. However, we are able to list, or we should be able to list, all possible outcomes, like rolling a die. We can list the outcomes 1, 2, 3, 4, 5, and 6, but we can't say exactly which one we're going to get. Okay, so a specific outcome is not possible to predict. It's uncertain what it's going to be. However, all the outcomes, we say that they are well defined. In other words, we know what they are and they can be listed. Again, like the die. Now, let's look at how we can actually go about illustrating these outcomes. You'll recall from the section on types of data, I used this example with the cars, so I'm going to go back to it. So let's suppose that we have this selection of cars, and I'm going to fence them off in that rectangle, and I'll call that my sample space. Now the sample space is denoted by a capital S, or this sign over here, which is a capital Omega, and it is a Greek letter, just like the population parameters. Right, capital Omega is a Greek letter, and we use either capital Omega or S to denote the sample space. We don't write sample space every time. Right, another sample space will be the set of all possible outcomes. Right, so whatever experiment we're performing, whatever we're observing, the sample space will contain all the possible outcomes that we can get. Now this diagram, the rectangle with all possible outcomes inside, denoted by a capital S or omega, we call that a Venn diagram, just as it is here, exactly with the rectangle and either capital S or omega. Now if we select one element in here, then we'll call that a simple event or an elementary event. So a simple or elementary event is an individual or single outcome. There's only one element. If we select two or more simple events or two or more elements, then we have what we call a complex event or a compound event. So we can either have a compound, in other words a complex event, if we select two or more elements. If we only select a single element or single outcome, then we have a simple or elementary event. Now, this should look familiar. Our events are denoted by the first capital letters, and I'm going to write here usually. It's not always the case, but it is usual. Right, so first letters of the alphabet, capitals, we use to name our events. Okay, that's what it means here. Events are denoted. So we'll name our events with the capital letters of the alphabet. Now this should look familiar because we did something similar for the variables when we looked at types of data. And then the individual elements inside of the event, we'll denote those by a lowercase version of the capital, and it will have a subscript that will denote the number of the element. So this is the first vehicle, so it's going to be a subscript 1 because the lowercase a falls inside of the uppercase A. Right, the capital A. Okay, so very quickly, this was the Venn diagram. Contains sets of all possible outcomes denoted by capital S or omega, and we can define events on here. In other words, we're just grouping together outcomes that we are interested in. Okay, an event, whether it's a complex event or whether it's a simple event, the reason why we have those events is because those outcomes have a characteristic that we are interested in. So for example, event A, the main characteristic of these cars are that they are all blue. Okay, so I'm interested in the blue cars, so I've grouped them together. Right, let's have a look at another example for a Venn diagram. We roll a fair six-sided die. So our Venn diagram will just be a rectangle, and it will contain the numbers 1 up to 6. Okay, 1 up to 6, because we're rolling a six-sided die. Now again, we will denote it either by a capital S or a capital omega. I'm just writing both here so that you can get used to the notation, but we use one or the other. And our sample space, a numerical form, will be written in this way. We will have curly brackets or braces. Okay, I'll start calling them braces. So we'll have braces, and inside we will have the list of elements separated by a comma. Okay, so this is just a numerical version of my sample space in Venn diagram form. Now, the sample space is also called the certain event. Now, this is very obvious. Why it's called the certain event is because if you're going to roll a six-sided die, you're definitely going to get one of these outcomes. You don't know which one, you just know that you're going to get one of them. So you are absolutely certain that one of the elements in this list is going to appear. And how events work is if you get any one of these elements in an event, then we say that the event has occurred. So I'll roll the die, I might get the number 5, so that means the sample space has occurred because one element in that event has occurred. I can roll the die again, I'll get the number 2, and that means the sample space has occurred. Right, now let's define another event, and we'll call it capital E, and we'll say that's the event of getting an even number. So numerically, it'll be braces, and in between I'm going to write 2, 4, 6 separated by commas. So if I roll the die and I get the number 2, okay, if I roll the die and I get the number 2, because number 2 falls inside of event E, I will say that event E has occurred, or the event of an even number, and the same for 4 and 6. If I define O, like capital O, to be the event of an odd number, then numerically it's going to be the list of numbers 1, 3, and 5. So if I roll the die and I get maybe the number 3, then I can say that event O has occurred because one of the elements inside event O has occurred. So that's why event O has occurred. Right, thirdly, let A be the smallest numbers, 1, 2, and 3. So again, numerically, write it in braces. And on my Venn diagram, I will just draw a shape around 1, 2, and 3 and label it capital A. And let B be the event that a 7 has occurred. Now, we don't have a 7 on the Venn diagram because it's for a 6-sided die. So that means event B is an impossible event because it can't happen on the sample space that we have. Now, if we have a look at outcome 2 or element 2, we'll write it in braces to show that it is an outcome in a sample or an element in a sample space. And if we look at the position or the location of 2, then we can see that it is shared by event A and by event E. So we say that 2 is the intersection of A and E, and we denote it by this upside down U, or this arch. Okay, that denotes an intersection, which simply means the elements that are shared between the two events that's joined by that intersection sign. If we look at the outcomes 1 and 3, 1 and 3, where are they? They're sitting in event O, but they're also sitting in event A, so that means that they are being shared by events O and A, so they are in the intersection of O and A. If we look at the numbers 1, 2, 3, 4, and 6, so that's 1, 2, 3, 4, and 6, then we see that it is everything that is inside of A and also inside of E. So we say that it is the union of those two events, A and E. And we write it as A union E. So this looks almost like a U, but it doesn't have the line on the right hand side. It's just the curl part. Right, now you will notice that in the union we have 1, 2, 3, 4, and 6. Now 2 is part of A and it is part of E. However, you will notice in here that it is only written once. And the reason for that is because there is only one 2. It is only this one that's being shared. So we don't write it twice, because there isn't really 2 of them. There's only one. Right, what about 4, 5, and 6? 4, 5, and 6. Well, if we have a look, then A is 1, 2, and 3. 4, 5, and 6 are the only 3 that's outside of A. So we can say that the event 4, 5, 6 is the complement of A. And there's a few ways in which we can denote it. We can say that it's either A prime, or A with a superscript C, or A with a bar on top, or there's another one, we can actually say not A. So it's just the opposite of event A that's occurred. Right. If we have empty braces, then it means we're looking at the empty event, and it's denoted by an O with a forward slash through it, or a 0 with a forward slash through it. And that's the empty event. So an example of an empty event in our case will be O intersection E. Because O denotes the odd outcomes, right? The event that contains the odd outcomes, and E denotes the event that contains the even outcomes. So there's nothing that's being shared between them. So if we take the intersection, we can say that it is empty. Now, because they have nothing in common, we say that they are disjoint events. We can also say that they are mutually exclusive events. Right, so these two, disjoint and mutually exclusive, are both terms that mean that nothing is being shared between these two events. Now these are the three basic operations. We have the intersection, we have the union, and then we have the complement. And with these three, we can do everything that we need to do. Right now, just like with arithmetic, where you have addition, subtraction, multiplication, and division, and you have rules that guide those operations, the same with event operations. We also have rules that guide them. So here's a list of the operations. The three most important ones here is called the associative laws. That's number 2. This is the first part, and that's the second part. The commutative laws, first part, second part, and the distributive laws, first part, second part. Now these three should sound familiar because you have exactly the same for your arithmetic that you learned at school as well. Now just to illustrate very quickly, if we have a look over here, A union A complement is S. Well, let's see what that means. If we take our sample space and we define an event on there, which we'll call event A, then everything inside of this event will belong to A. Everything outside of it, right, everything outside here will belong to A complement. So when we combine A with A complement, in other words, when we list all the elements that's in A, and we combine that list with the list of all the elements that's not in A, then we'll get our sample. If we have a look at this one over here, then we can draw a little Venn diagram, which will be our sample space. We'll define an event A on there, and what this is saying is if we take event A and we look at what is being shared with the sample space, then it'll just be A. So if we look at everything that is in A, it is also in S. Right, so as I said, these are very straightforward, nothing tricky about it. Right now, for the examples that I've mentioned so far, we had only one stage or one trial. In other words, we rolled a 6-sided die only once. Let's consider a case where we flip a coin 3 times. So now it's not just heads or tails. It's going to be a sequence of outcomes. So in this case, we consider what we call a tree diagram. Now, tree diagram is what we use to represent multi-stage experiments or experiments with multiple trials. Right, so hence we flip a coin 3 times. Now on the first flip, we can either get a head or we can get a tail. On the second flip, we can get either a head again or a tail again. On the third flip, we can get either a head or a tail again. Now, we've flipped it 3 times and we have this list of outcomes. But keep in mind that in this tree diagram, we follow each of the branches to get to these final outcomes. So if we look at the top one, then we have a head, and a head. So that means after flipping the coin 3 times, we can end up getting 3 heads in a row. Another alternative will be getting 2 heads and then getting a tail. Another one would be getting a head, then getting a tail, and then getting another head. The point is, we have 8 outcomes. Okay, so it's just these 8 dots that I've made over here, right? These 8 outcomes, or these 8 elements. Now, if you think back to what I mentioned when I looked at types of data, then I said that we usually just list the outcomes or the elements, and that does not mean we have the data. Only when we start looking at what are the things that describe those elements, then we have data. So in this case, each of these outcomes are made up of 3 parts. Okay, 3 parts. So each of these describe the outcome. So in this case, 3 heads describe the first outcome. 2 heads and a tail, that describes the second outcome. Head, tail, head, that describes the third outcome. And then the last one we have 3 tails, and that describes the last outcome. Now again, if you think back to what we did in types of data, if we took one of the cars, then we had four things describing it: the color, the age, the distance, and the risk. And because we had four different things describing it, or four different characteristics, or four different variables, we said that it was multivariate data. Because each outcome, okay, you can think of this as my outcome, had four things describing it: the color, the age, the distance, and the risk. So you should notice the similarity between these two. So that's why here we say that we have multivariate data, because we have three things describing one outcome. Right, so we have a multi-stage experiment. A tree diagram is the best way to illustrate that multi-stage experiment. When it is an extensive experiment, then it's not always possible to draw a tree diagram, but it does give us an idea for simple cases like this. Right, we have these different branches, each branch leading to a different outcome, and each outcome is described by a few components or a few variables, which makes it a multivariate data set. Now, if we take those outcomes, we can write it in the form of a Venn diagram. So we'll have it denoted by a capital S or a capital omega. And now we can start defining events. So let's say that I'm interested in the event E1, and I'm defining it to be the event of getting one head. Then I'll identify all the outcomes that contain one head only, and I'll group them together, and that will be my E1. If I'm interested in event E2, which is the event of at most two heads, okay, then at most means two heads, one head, no head. So I'll identify all the outcomes with two heads, one head, and no head. So here I have 2, 2, and 2. Here I have 1, and here I have none. Now you'll notice that event E1 is contained inside of event E2, and we have notation for that. It is the intersection and union sign lying on its side. It means that E1 is a subset of E2. In other words, E1 is inside of E2. Right, the next part looks at tables. Okay, now I'm going through all of these different scenarios just to illustrate where we can have events, or where we should be able to identify events. And just because it is not written in the form of a Venn diagram or a tree diagram doesn't mean that we don't have events that exist in that scenario. So if we consider the data set from the earlier lessons, right, the 20 observations, and remember capital X denotes the entire data set. This was the one with the values from 0 up to 290 if I remember correctly. Then what we did was we sorted it into our frequency table. Right, the data was sorted into a frequency table, and we had these classes, and we counted how many observations there were in each. Now if I were to take each of these classes, and instead of writing the boundaries, I'll write E1, E2 up to E5, then what I've created here are essentially events. This is the event of getting a number in that interval. E2 is the event of getting a number in that interval. E3 the event of a number in that one, and so forth. If I look at rewriting this data set, then I can write it in this form, which looks almost like a Venn diagram. I'll denote it by a capital S just to give that impression, and I will create events on here. So I'll group together everything that is grouped together in my frequency table. So that means that this frequency table contains events. I can write it in this way. Now please note that we never have duplicate values in a proper sample space. Okay, here I have duplicates and triplicates. We never have this scenario with a proper sample space. We always just write down the element once. That's really, really important. Elements are only written down once in the sample space. However, I'm leaving it like this for this in this case because at a later stage in the next section we're going to be looking at probability and the two ways in which we will calculate probability, and this has to do with one of those ways in which these duplicates will become one, but the probability will indicate, or the relative frequency will indicate how many outcomes there actually are. Although we only listed once, the weighting, which is the probability and the relative frequency, that will change. So if we look at our operations, E1 intersection E2 will be empty because the event E1 is bounded by 58.5 and E2 is also bounded by has a lower bound, 58.5. So everything in E1 cannot be in E2 and nothing in E2 can be in E1. So there is no intersection there. We can see it over here as well. This is E1 and E2, there's nothing being shared. If we take the union of the two, then it's going to be 0 and 70 that we're going to write together. If we look at the complement of E4, this is E4, so the complement of it will be everything outside of E4. Okay, it doesn't matter whether it's in events or not, it doesn't matter whether it's in intersections or unions or whatever the case is, it should not be in E4. If it's not in E4, then it's in the complement. If we go to our histogram, then we have exactly the same situation. Remember, the histogram is just the graphical representation or the graphical version of the frequency distribution. So the rows in my frequency distribution, those classes, will be the classes on my x-axis over here. So each of these will be an event as well, which is represented by these events on the Venn diagram. Right, if we consider charts, okay, this is a simple bar chart, and these are responses on a questionnaire, and the options were never, almost never, sometimes, often, and always. And we had the number of people selecting these options. Then each one of these can also be considered an event. All of them combined will be the sample space. Right, now the last one is what we call contingency tables or cross tables. Now, cross tables or contingency tables is not for univariate data, it is for bivariate or multivariate data. Now, in this case, we have bivariate data on the table. Now, how can we say that we have bivariate data on the table? Well, it says here, consider testing patients for the presence of a disease, and the results are on the table. So there's obviously 1,000 people that was tested, and the test result is the one variable, and whether the person has the disease or not is the other variable. Okay, so there's two variables. If we take one person, let's write here person 1, then person 1 can be described by two things, x and y, and x will be the test result and y will be whether they have the disease or not. Now, please note, the reason why these types of data sets exist is because medical tests are not 100% accurate. Okay, a lot of the tests, or all the tests basically, will sometimes give a positive result when the result is actually negative, then will give a negative result when the result should actually be positive. Right, so that's what this table represents. So we have each person, this is going to be person 1 to person 1000, and each one of these will have a test result and whether the disease is present or not. So the test result can be either positive or negative, and the presence of the disease can be either positive or negative. But the point is, we have bivariate data on the table because we have a column and we have a row. Right, now if we consider these 1,000 people, then we can see that they're split between these four categories over here. We have 76 people that test positive and they have the disease, 92 which test positive and they don't have the disease, 4 which tested negative and they have the disease, and 828 which tested negative and they don't have the disease. So the 1,000 people are contained on here. So what I'm going to do is I'm going to represent it as a Venn diagram. So drawing my rectangle around it, and here I have 76 people, so I'm going to make 76 little dots over there to represent the 76 people. Then I will have the 98 dots over here to represent those people. I'll have the 4 dots over there, and here I'll have the 828, and of course that's my sample space. Now if you think of what we did in the previous slides, then grouping all of this together will give me the event which I called A, and this is the event of a positive test result. Okay, this is the event of a positive test result, but I just grouped all those people together. Then over here, this is the event of a negative test result. So you can see events A intersection B will be empty, because you can't have somebody being tested with one test and then the test showing both positive and negative. One test can only show one result. So a person will be classified either positive or negative, but not both. So they are disjoint events. We can do something similar for the rows. Let C be the event of the person having the disease and D be the event of somebody not having the disease. So you either have it or you don't. So these two events C and D, if we take the intersection, also it will be empty. So C and D will be disjoint. A and B will also be disjoint or mutually exclusive. However, if we look at A intersection C, then it's this yellow area over here, because you can have somebody that tested positive and have the disease. The same with the others. You can have somebody that tested negative and that has the disease. So this is not empty. This is not empty. And the same for the other two. You can have somebody that tested positive and doesn't have the disease. You can have somebody that tested negative and doesn't have the disease. So these 4 values that we actually have on this table represent 4 intersections between the 2 variables that describe the data set, the test result and the presence of the disease. Right, so in summary, we have a Venn diagram for representation of our outcomes. The Venn diagram is just a rectangle. We call it our sample space, denoted by a capital S or omega. Omega is of course a Greek letter. If we define certain characteristics for our elements, then we can start grouping them together according to those characteristics. And those groups, we'll call them events. If there's only one element, it'll be a simple or an elementary event. If there's more than one, we'll call it a complex or a compound event. Events are usually denoted by capital letters from the start of the alphabet, like A, B, C, D, or E. Very seldom that we will use other letters, but it is possible. Then each element inside, just like in the case of variables, we denote by a lowercase with a subscript. Lowercase, which is just a lowercase version of the uppercase name, and the subscript to say which one we're working with. And then, very important, we have a random experiment or random observations. That means we cannot predict a specific outcome, but the outcomes are well defined, which means we know what the outcomes can be and we are able to list them. Right, this is very important, all of this in this section. It will be coming up repeatedly for the rest of the course.